All right, everyone, come together here. Hopefully, all had a good weekend. I didn't do anything, so I didn't bring grades, but I got your quizzes graded. I'll hand them out towards the end of the class, so we're not, just staring at the quiz during lecture. Okay, so. The second active homework is published. I'm going to put in the scores for the first homework. So if you need to submit it late or need an extension, let me know so I don't give you, a lower score than you ought to receive. And then the second homework is posted. That's going to be tentatively due. We're going to set a due date for that next Tuesday, I think the 2nd. And that's because we'll finish acid and bases by today. So we don't need to worry about that next week. Okay? So there's a quiz on Thursday. So study drawing skeletal structures from formulas and condensing said structures using condensed formulas. Okay, and resonance. So study up on resonance, be able to draw resonance structures, valid ones, okay? Ones that don't disobey the octet rule. That's the main argument here. You want to draw good structures that don't violate the number one guideline, which is the octet rule. Or, any normal bonding patterns we've seen, okay? But are there any general questions before we begin? No? So in lab, another dry lab, I'm thinking about doing incorporating some lab techniques before we actually get to any of the experiments. So I'll keep you updated on that. But this week is a dry lab, hybridization, and we're going to start talking about how alkanes can rotate in space. So that's called conformers. Okay? All right, if there's no general questions, I will pass out attendance. So please sign in once you get the attendance. All right, where did we leave off? Okay, so we left off, I think we stopped at talking about. Oh, yes. I got water bottles. So, guys, don't forget your water bottles. Sometimes we'll remember to pick it up and keep it safe for you, but you never know, okay? So just be careful of that. All right. So I believe we stopped at acid and base. How do you tell if something is stronger, acid or base? And we looked at resonance. Are there any lingering questions about that? I think we just need a little more practice, so we're going to do a lot more practice today. Okay? All right. So there's the fourth thing we look at. Okay? So we're going to look at now. We're going to look at electronegative atoms. Okay. So electronegative atoms. All right, I like to say that these are when they are nearby, okay? So we have a specific name for atoms that like to withdraw or hold on to electrons from other atoms, okay? Or the negative charge. Those are called electron withdrawing groups. Electron withdrawing groups. Okay, so you'll hear throughout this class I mentioned electron withdrawing group, EWG, or electron donating, EDG. Those are two terms we use when we're talking about induction, or when the charge is being released or polarized or pulled away from atoms or another part of the molecule. Okay? So what do these do? They increase the acidity of a compound. All right, so let's look at a few examples. So we have normal acetic acid. So let's just draw acetic acid here. Okay. Oops, no, don't solve. All right. So this has a pKa of 4.76. Okay. But if we add an electronegative atom on the carbon atom, right, on the CH3, say we substitute a hydrogen for chlorine, we'll see that the acidity increases. So let's put a chlorine here. Chlorine is fairly electronegative. And then we're going to put our carbons here. And then we have the acidic hydrogen that we're comparing our pKa's to. Okay, so this pKa is actually more acidic. So this pKa is almost 2 pKa units lower. So it's almost 100 times. Well, I'm not exactly sure it was exactly 100 times, but it's a logarithmic power of 10 increase in acidity. So very acidic here. So this is an acid that's fairly strong. Okay. And we usually don't work with this one in Gen Chem, but it's stronger than acetic acid, but still considered a weak acid if we compare them to the mineral inorganic acids like HCl. Okay, so we see this effect because if we imagine this hydrogen, the hydrogen up there falling off, we'll get the conjugate base, which is O minus, right? So we'll get an O minus charge. Now what stabilizes charge? We just saw resonance does, but also electronegative atoms, or the term we like to use, electron withdrawing groups, and that's the chlorine. It can be chlorine, oxygen, fluorine. Those are the pretty common ones. Nitrogen can probably help too, but it's usually chlorine, fluorine, or oxygen at that position. Okay, so let's see now what happens if we add a more electronegative element, and what happens when we have more than one of these groups substituted for hydrogen. All right, so let's look at the fluorine example. So fluorine is more electronegative than chlorine, so we should probably see a stronger effect for the acidity here. All right, so we're comparing this hydrogen again. So this pKa is even lower, but not that much lower. Still lower though, by almost 0.2, almost 0.3. And then let's compare 2 chlorines now instead of 1. All right, so I'm just keeping drawing out the lone pairs just for now. When we get to later chapters, like chapter 3, I probably won't draw it anymore. Okay, so if we compare the acidity to this hydrogen, what do you guys think? Lower than the one with fluorine, or higher pKa than the one with fluorine? Lower, good. So this pKa is very low, almost negative. Okay, so this pKa right here is 1.25. So this is the strongest carboxylic acid out of all of these. Okay, so normally you see these acids not in like production, or it might be used in industry to make like goods. But I doubt you ever see this in like the food industry or agriculture. These acids are mainly used as catalysts, acid catalysts. So you need a hydrogen to promote your reaction. Usually these are some of the reagents you may use just because a procedure calls for it, or everything's in one phase, etc. All right. Okay, are there any questions about this trend?
Does it kind of have to do with like the
Yeah, right. So it's pulling electrons. So
That's why the chlorine is the strongest acid, because it's pulling on.
yeah, so the more of those you have, you're going to pull more of those electrons away from the OH bond, and that kind of makes it easier to donate its hydrogen. Yeah, you got it. All right, so that's kind of like induction effect. If you ever took physics, you might have heard the inductive effect with charges, and that's the same kind of idea. You have a separation of charge, and you can pull it one direction by having a certain group here, electronegative group, that will pull those electrons away and stabilize the conjugate base. Okay? All right. Okay, we should go now to the last trend here, or the last bullet point. And then we'll do an exercise, and then we'll talk about bases. How do base strength, how does that correlate? Okay? So let's go to letter E. Okay? So let's do the opposite. So the presence of electron donating groups. So what this does, it releases electrons. And normally these groups are when you have something that's not very electronegative. So it doesn't like to hold on to its electrons. And that's usually given to carbon groups. So anything with carbon, any carbon chain, it doesn't matter if it's length, it doesn't matter if it's a long chain or if it's branched, it will release electrons because carbon doesn't like to hold on to its electrons very well. That's why they give it up in compounds with oxygen, nitrogen, chlorine. Okay? So what happens here is that the presence of these groups decreases acidity. Of a compound. All right. So we'll use these two examples. Well, we saw in a previous example, right? If we just had hydrogens there instead of chlorine atoms, the pKa went up. Okay, so that kind of tells you that carbon groups or hydrogen with there, if you don't have anything pulling those electrons away from the conjugate base, it tends to be less stable and higher pKa. Okay, so let's use that same example we had. Acetic acid. And again, we're comparing that hydrogen right there. All right, so pKa here. Okay. Now let's just have the, this is now formic acid. All right, so very similar to acetic acid, except you have one less carbon atom. All right, so this pKa is actually more than 1 unit less, 3.55. Okay, so that tells us that these alkyl groups, or those carbon groups there, they destabilize the conjugate base. So if we kind of visualize that, say we have our conjugate base here. So we have our H3C, okay? And say we have our conjugate base. It's O minus, right? So you can stabilize that O minus if you can somehow share the negative charge with other atoms through resonance, like we saw before. And then if you have electronegative atoms can pull that electron away from the oxygen and it'll be more happy because it's spread over now more atoms. However, when you have a carbon atom, if we think about the charges here, this is partially positive, partially negative. And now the electrons around carbon, there's going to be a partially negative charge here because there's electrons associated with it, right? And what you guys think is going to happen? It's going to be attracted to the positive carbon. So it's going to pull away those electrons. And if we have, now we're going to have a carbon atom that's right next to the oxygen with a more partially negative charge. So now this turns into a partially negative charge. Okay, so now it's partially negative. Okay. And when it's next to this oxygen, they're going to clash here. So these charges are going to repel, and that makes this unstable. Okay? That's what we mean by induction. You're going to create partial charges, and if you have something that has electrons, it's going to donate to the carbon atom next door. And that charge is right next to the negative charge on both of those oxygen atoms. That's going to destabilize your structure. So you don't like charges next to each other, right? They tend to repel. So this makes this unstable. That's why the pKa is higher. The acid does not prefer to donate this hydrogen as easily as formic acid. Hydrogen, you don't have that same kind of effect because hydrogen barely has any electrons associated with it. So it won't, you won't see that effect happen. Okay. All right, so that's the unstable argument. So the next thing I want to write here is explain what is happening here. So alkyl groups. Okay. So alkyl groups are basically any carbon group here. So like CH3, CH2, CH3. So any group that looks like this, any chain of carbon atoms, etc. here, they tend to release or push electrons toward another atom. Okay? So the reason why H doesn't do that is because H only has one electron to share, so it doesn't have the ability to supply much electron density. Okay, so H is not a good source of electrons. Okay. Because only has one. All right, it only ever has one electron associated with it, right? But like kind of localized or around itself. It shares another one with another atom, but there's hardly any electrons, so that's why H is kind of neutral. It's neither donating or electron withdrawing. Okay. Are any questions about donating? We'll come back to this frequently, okay? So just think, if something's not electronegative, it's not going to stabilize a negative charge particularly well. So any nearby atom there won't help the acidity. It'll make it worse, okay? Of course, our benchmark was acetic acid. So if we go to something that's not as electron donating, H, pKa goes up. And then when we go to something very electron withdrawing, the opposite, more electronegative, pKa goes down. So it's more acidic. Okay? All right. So these are some trends to think about. Okay? And the homework, there's some questions on there. I'll pose you some questions where you have to consider these trends, okay? And they have an acronym for all these trends combined. It's called CARIO, okay? So you have to consider charge, atom size, okay, resonance, induction, and then I forgot what the O is for. But it's found in these bullet points that we mentioned. Are there any questions about any of these bullet points? If not, I'm going to do an example. Okay? All right. So let's go to an example here. So Here's our exercise. Let's rank the following compounds in order of increasing acidity. All right. So here I'll tell you that if you write something that's first, that means that's the strongest acid, okay? So you can just use numbers. 1 is strongest acid. Okay? And then number 4 is going to be the weakest. All right, so we're going to have a series of rings here with an OH on it. All right, there's 1. Sorry if I can't draw here. Here's the second one. All right, here's a NO2 group. All right, so I'll explain what NO2 is. It's a specific type of group. One of those groups we just talked about. All right. So let's put the lone pairs on here just to show how it reacts, okay? All right. So all these groups are very similar. You have a ring and the OH, and then some other groups attach on the ring, okay? So let's first get out of the way what NO2 is and what it looks like, okay? So NO2 is one of the most powerful electron withdrawing groups, okay? So NO2 it looks like this. All right, so here is the point of attachment to the ring. Here's N, O, and then O right here. Like that. All right, so this is what we call an electron withdrawing group. And I'll show you how it works, okay? So, to go about this, you have to consider a few things, all right? So, number 1, you should look for electronegative atoms, okay? So, look for electronegative atoms, okay? All right. 2, all right. So, we notice that our hydrogen is on oxygen, so criteria 1 is complete. We consider that hydrogen, okay? 2, resonance. All right. Out of all of these here, which one does not have the possibility of resonance structures? All right, you could go first, second, third, and fourth. The third. So we can actually just say that one is what? The weakest or the strongest? The weakest. So let's put this guy as number 4, okay? So this has no resonance. So I'll just put this in parentheses. No resonance. All right. Now our job is a little bit more tricky, okay? Because now all these other ones have resonance. So what's the last criteria we should look for? Right, so any electronegative atoms or electron withdrawing groups nearby, okay? That's our key here. Electronegative or electron withdrawing groups nearby. All right, so 2 of them have electron withdrawing groups, but 1 doesn't. So we can actually place the second weakest now. Which one is that? The first one. So put number 3 right here. All right. Now it's kind of hard to say which one is number 1, which one is number 2. So you can't just look at it. when you're first learning about this, right? So you actually have to go and draw some resin structures. So let's look at the second structure where the NO2 is a bit closer to the OH group. All right, so let's just draw here. So when you're comparing resin structures, always draw the conjugate base, okay? So let's do that here. All right. All right, so I'm going to take off the hydrogen and create my conjugate base. So negative charge right here. And then the nitro group is going to be right there. All right. So for now, I'm going to include the lone pairs just so we're familiar with this, okay? All right. Okay. So the nitro group is there for a reason. Through resonance, it can withdraw or basically siphon off electrons through the pi bonds and make that negative charge more stable because you're sharing it with other electronegative atoms. So that causes the acidity to go way up because your base is stable. All right. So we're getting used to these arrows here. So you're going to move them down here, form a double bond. Now I'm going to rotate the bonds in the ring. So sorry if you can't see this. And then I'm going to take this bond, move it outside. Oopsies, undo that. Take this bond, move it over here. Okay. Does that make sense? I just moved it to form a double bond with nitrogen. Okay. And then I move this bond out here. Okay. Now let's draw the resulting resin structure for that one. All right. All right, so if I follow the arrows, there's a double bond here now. Double bond here. Double bond there. Now there's a double bond outside of the ring. Okay, now there's an oxygen with a negative charge here. An oxygen with a negative charge here. And then the nitrogen still has the positive charge because there's still 4 complete bonds around it. So it still has an octet. All right. So we see here the charge where it was successively transferred through the ring, and now it has been placed on the nitro group. Okay. So that's how electron withdrawing groups stabilize or withdraw electron density from an atom to stabilize it. Okay, so that's called delocalization through resonance. All right, so, well, it looks like this position where the NO2 group is, it might somehow affect how the charge moves through the ring. Okay, so here we could say the negative charge. So negative charge. Oops, sorry, I can't speak English today. Shared over multiple atoms. So this is stable. Okay, so now let's do a different analysis here. Let's say we now don't look at this structure, structure 2. We're going to look at structure 4. Okay. So now we're just going to do pretty much the same thing, except the nitro group now is just in a different position. So we still have our O minus here. All right. And I'm going to draw it like this. Okay, draw it downwards like that. Okay. So you guys try moving the arrows. Can you move the arrow? Can you move the electrons that was once in the ring outside to the nitrogen? So think about how I moved them. Think about how I moved them before. See if you could do the same thing with the nitrogen and the nitro group out there. All right, so we try to move them around, right? We'll notice here that if we move that arrow down towards, the southernmost carbon right there, the double bond right next to it, can you move it outside? Can you do this? What's going to happen if you do that?
It's gonna make the
Are we violating any rules?
yeah.
Yeah, so we can't do that because that will violate the octet rule. So you see that no matter what we do, we move the electrons around, we cannot move it outside to the electron withdrawing group. So even though there's an electron withdrawing group there, it does stabilize the charge due to how far it is away from the charge. There's some stabilization there, but through resonance, which remember, resonance was higher in the list than say electron withdrawing groups. Resonance has higher priority, so the resonance effect is more is predominant in this case. So it has a higher, it factors in higher for determining how strong an acid is. Okay, so this can't do that. So let's undo that arrow because we can't do that. This has to, unfortunately, go over here. We have to put it on a carbon atom. Okay? So now let's draw the resulting structure. All right, so let's draw the resulting arrows. All right. We have arrow there, there, okay. All right. So the charge here, if we compare the negative charge, well, in this structure, where's one of the negative charges on? What kind of atom? Which atom? We see one on oxygen, but where else?
On the carbon.
On the carbon. And we compare the structure above, where are the negative charges? Both on oxygen. So one's clearly the winner because we don't like negative charges on what atoms?
On carbon.
Yeah, atoms with low electronegativity because they can't stabilize that charge as well. Okay, so here, that's the difference here. I would say here negative charge is on carbon and can't or cannot move outside to the nitro group. All right, let me just explain what nitro. This is nitro. All right, so that's why now we have a clear winner. Which one's number one? The second one, and that by what's left. This is number two. All right. So that's one of the ways we'll have to be able to distinguish between acidity here. Are there any questions? So guys, do the homework. Good practice. Okay. So yeah. So acidity will probably be the next, not this upcoming quiz, but the next after that. Okay. So do some of the homework problems for that. All right. But are there any questions about the examples I just gave? Yes. Oh, sorry. Good. Thank you. It's still there. I forgot it. Yeah. We must conserve our charges because nothing happens here. Okay? Thank you. All right. Are there any questions about acidity? So those are all the Those are all the guidelines you have to consider when thinking about acidity. Okay, so but get started on homework. That'll get you thinking about how to approach these type of problems. Okay, so now let's switch gears here. Let's go to basicity. How do things act as a base? All right, predicting relative basicity. All right. So not as many trends here for basicity, but still we have to consider a few points. Okay, A. Electronegativity. All right. So the trend here. So how basic you are, basicity. Okay, decreases as the electronegativity of the atom accepting a proton increases. Because if you decide it's too electronegative, does it want to give up its electrons? No, right? So you're too electronegative, you're becoming more of a hog. So it hogs electron to itself. So fluorine is a good example of this. It is basic, but if you compare it to stuff like oxygen and nitrogen, it's less basic because of its electronegativity. All right, so here's the trend. So let me draw an arrow going this way. Okay, so we have CH3 minus, NH2, 2 minus. Oh, sorry, no, just two set of dots. My bad. I meant to draw a negative charge there. And then OH minus 3 lone pairs. And then, of course, fluorine here has an octet. I mean, it's charged with no bonds. All right. So here, this way, we have increasing En. All right, electronegativity. All right, and then the other arrow, we're going to have increasing basicity. Okay, so carbon is the most basic. All right, that makes sense. It wants to form all bonds around it, and it really doesn't want a lone pair, right? So it wants to share its electrons. It has no preference to keeping some electrons to itself as a lone pair, unlike nitrogen and oxygen, right? And of course, fluorine likes 3 lone pairs and then just 1 bond. Okay. All right. So let me give you some examples. CH3, NH2. So methylamine is more basic than methanol. So you put methanol in water, and you put methylamine in water, take the pH, you'll see methylamine will turn litmus paper blue. Methanol will just stay neutral because it's like water. It doesn't do anything. Okay, so that's how we can tell that basicity follows this trend. All right, and then there's also basicity associated with the hybridization. All right, so let's do methylamine again. All right, so this nitrogen on this methylamine, the nitrogen, what hybridization is it? What model? sp2, sp3, sp? sp. What do you guys think? All right, so that nitrogen looks like it has all single bonds and a lone pair. All right, I heard 2, not 2. sp3. All right. Now we have a double bond in there. What is the hybridization? sp2. There you go. All right. Oops. All right. So the lone pair on the left is more readily available. That's what we say. Remember, if something is more hybridized or has more S character, the electrons on that atom, that lone pair, is held more tightly to the nucleus. So those are more stable. So they are not available to act as a base. You can't donate those electrons to form a bond to hydrogen. All right, so here we could say electrons on this side are held more tightly, okay? All right. And we can say here, just to reiterate, more S character in orbital, in sp2 orbital. Remember, guys, the more spherical your orbital is, the more likely it's going to be closer to the nucleus, so the more stable it'll be. All right? Okay. All right, that's trend A. Are any questions on that trend? Think about if the electrons are held less tightly, less electronegative, further away in a more p character orbital, sp3, you're going to be a better base because you can better donate those electrons. Okay? All right. All right, that's trend A. Now let's talk about B. Okay. So let's talk about electron withdrawing groups and donating groups. So the presence of electron withdrawing groups, okay, EWG, decreases the basicity. So if we compare that to acids, that kind of looks like the opposite trend, right? Electron withdrawing groups made a stronger acid, but now they decrease the basicity. Why might that be? Anyone have any ideas? That's not a bad argument. If something's more acidic, then it must be a weaker base, right? That's not a bad argument. So let's just think about how it looks like. So here is a chloromethylamine. So the electrons in question are on the nitrogen because that's the most basic atom. All right, so this is actually less basic than regular old methylamine. All right, so remember, to act as a base, the lone pair on nitrogen must be available to donate somewhere else. So what happens when you put an electron withdrawing group nearby? What's going to happen to those electrons on nitrogen? Are they going to stay there? Or are they going to be moving towards somewhere else? All right, let's do this. So I drew a dipole moment. When chlorine's there, it's going to change the dipole moment between both nitrogen, hydrogen, and nitrogen and carbon. So those electrons are actually going to be pulled towards the chlorine, okay? So those electrons are going to be moving this way. The electron density is moving this way, okay? Based on this arrow. So when they're moving there, they're not available for nitrogen to act as a base. So that's why it's less basic, All right, you have electrons moving away from nitrogen, including the lone pair. All right, so electrons can now possibly be found more closer towards chlorine now and the carbon because of this effect. All right, so that's the rationale there. Okay. Now, what about donating groups? What do you think happens when there's a donating group nearby? Yeah, good job. All right, this is abbreviated as EDG. Okay? All right, so this increases the basicity. All right. So what do carbon groups like to do? They don't like to hold electrons, right? They like to do what? Donate them, right? Give them away. They're good Samaritans here. They like to share with everyone, okay? So the more methyl groups or the more carbon-based groups you have nearby a basic atom, it's going to donate those electrons and make this lone pair seem like it has more electrons nearby, okay? So remember, let's draw our dipole moments again. So the electron density is going to point towards the nitrogen in both of these bonds from carbon, all right? So there's going to be increased electron density on the nitrogen. If you gather enough electron density there, it's going to want to give it away because it's too much for the nitrogen to handle. So that's why these are better bases if you add methyl groups on the nitrogen instead of hydrogen, okay? So this is much greater, better base than just say a singly methylated nitrogen amine here, okay? So here we could say more electron density around nitrogen. Okay, so those are the trends. Bases are better if there's no electronegative atoms near the base, near the atom, donates electrons. And it's better base if the groups around nitrogen are carbon atoms. Any carbon atom. It could be just a methyl group, CH3, or it could be a ring too. If there's a ring nearby, it doesn't matter. All right. Okay, so let's do a few more examples now. We're going to go using the electron donating group analogy to see how that affects acidity. And then we'll do one for bases, okay? So let's go on. No questions. Any questions? No? All right, so let's do another exercise here. Putting this concept of electron donating groups to practice here. So here's another exercise to solidify our understanding, which of the following molecules is the stronger acid? Is the stronger acid? All right, you have to explain. So let's explain. All right. All right, so we have a few of them here. All right, sorry. Erase that for now. All right, now we're going to have a different group here, OCH3, okay? All right. Okay. So which one of these is the stronger acid? All right. So we have to compare a few things here. Okay. So we know before that NO2 is what type of group? Electron drawing or electron donating? Well, drawing, and that favors acids, right? But you have to be able to explain, okay? So one thing I like to do is you can show that if I drew the conjugate base, it will be stabilized. The negative charge will be stabilized by the NO2 group. So we've seen that before, right? Oh, but we haven't seen it in this position, where the OH group and the NO2 group are on opposite sides. So let's draw that. So let's draw the conjugate base. Now we could draw this out again. Now this time I will not draw the lone pairs. We saw that before. O minus. All right. So we know here that we could form a double bond there. Boom. All right, let me put the charges though. Negative. Like that. Like that. So we've seen this before, right? That the negative charge can be placed outside of the ring and stabilized like that. Guys, what's important here is that you know where the lone pairs are and that you could draw the charges correctly. So if you know that, you don't have to draw the lone pairs every single time. Okay? So here we see negative charge is stabilized. Drew resonance. So we've seen that before. So we would expect that this is pretty much probably a stronger acid. But now we have to consider what the OCH3 does. Okay? So here, drew resonance, all right? So here we could think, okay, we could think that this is a maybe strong acid. Or stronger acid, okay? Now we gotta explain why the one on the right is not a strong acid, okay? So let's draw the conjugate base. And hopefully I have room here, but let me just move this over a bit. Guys, you don't have room, it's okay, draw it below. So, draw the conjugate base. All right. All right. But if we move these electrons, can we move it outside to the oxygen? What do you guys think? Remember, let's just draw this for clarity now. This has two lone pairs. The nitrogen and our nitro group on the left, right? It had a double bond, and we could move that. But can we do such thing in this structure on the right now? No. All right, so the best thing we could do is put these electrons, try to move it like so, okay? And we'll get something like that, right? Okay? You get that, that can happen. Or now let's say we go the opposite way, okay? So let's not draw a structure yet. So do we all agree those electrons can move like that? That's what you would assume if you had an acid, if you had an electron withdrawing group, right? Like NO2. But that doesn't happen here. So let's go back a bit, all right? Now, this is actually what happens. This is so, it is so willing to share, even though it's oxygen. It's willing to share because this group is right here. So this group is making that oxygen unstable and it wants to donate its electrons into the ring, okay? So this guy, this whole group right here, okay, so this whole group, OCH3 is an electron donating group. So has the opposite effect of the NO2, all right? So what actually happens is these electrons are going to move there, and this electron is going to move on top right there, and we can now draw the resin structure, okay? So that's now going to be a positive charge of a lone pair. Now this is going to be a negative charge, and you have oxygen with a negative charge here. All right, so what's wrong with this picture? Why would this not be as preferable as this structure right here? If you had to guess. So look at these two charges. Do they prefer to be next to each other? The two negative charges on this last structure. Look at these two charges right here. Okay. So two minus charges nearby. Okay. Unstable. Okay. So this would be a unstable, strong base. All right. So the fact you have this resin structure here, that kind of tells us this is not going to be an acid. It's going to act as a base instead. So this form is not particularly stable. So the acid won't form as readily. So this is going to be the weaker acid. Well, let's put that under here. Right here. Weaker acid, stronger. All right, and in this case, it's by resonance. It's the resonance effect. All right, so look at your conjugate base, the minus charge. If you can move that minus charge away from it and onto other atoms, like other oxygen atoms, better. If you can't move that negative charge and you're going to produce another negative charge right next to that oxygen with the negative charge, that's going to be a base, okay? So it's going to be a weaker acid. So that's the rationale there. Okay, that was a lot. Any questions on that? Okay, so let's do one more example, and then we'll take a little break. Okay. All right. Now instead of which of the following is a stronger acid, let's do stronger base. Okay. Two molecules is a stronger base. Explain. All right. So we have two molecules here. So I'm going to draw out the nitro group. All right. We have that one. So we basically have two substituted NH2 rings here. So this is called aniline. But don't worry about that name. All right, so let's just draw a lone pair here, just to illustrate. All right. So, which of the following is a stronger base? All right. So in both of these, which atom is acting as a base? Is it the N or is it the O? If we think about which one's less electronegative, nitrogen or oxygen? Nitrogen. So that's going to be our basic molecule, our basic atom. So we're looking at both of the nitrogens on the very bottom of the structure. Okay. So we're going to say N is a stronger base than O. Okay. Now we have to look at the resonance argument. Okay. So let's think about this one. All right. So on the one on the left, what's going to happen to the lone pair, unfortunately? Yeah, so it's actually going to be lost to the ring because of resonance here. So this one's going to go up there, up there, up there. All right, so let me just draw the resonance structure vertically here. Boom. All right. Like that. All right. So unfortunately here, the electrons on the nitrogen are going to be lost to the ring. So they're not going to be readily available for nitrogen to act as a base. All right. So here we're going to say electrons on nitrogen are shared across the ring. All right. So the electrons here are not available on nitrogen to form a bond to a proton. Okay. But let's see what happens here. So in this case, we have an OCH3 group and then an NH2 group. All right. So this can actually go either two ways. Nitrogen can do the same thing it did. All right. Or oxygen can do what we saw last time on the last page we did. Okay. So even though oxygen is more electronegative, that carbon group next to it is causing it to be reactive and donate its electrons across the ring. Okay? So remember, electron donating groups, they make atoms unstable, more electrons than necessary, and they will want to push it off somewhere. Okay? So this oxygen wants to push it off exactly as it did last time, and you're going to push it right next to this nitrogen atom here. All right. And if we draw the resulting resonance structure, we'll see, oh shoot, too close. Oh, I forgot I had that on. Yeah, I've been going to bed with my phone too close to my face. Not good, my eye doctor says. Okay. All right. So what happens here is that there's a negative charge on this carbon. So this is telling us that these electrons now are moving towards nitrogen. So there's increased electrons around nitrogen. That makes it a better base because there's more electron density, right? And remember, OCH3 is a donating group as illustrated by this picture. That's why this one on the right is probably the stronger base. Okay, so what I like to say here is that electrons are moving towards N. Okay? So, can act as a better base. Okay? So the movement of these electrons makes this structure here more unstable. So this is going to act as a base. Okay? Whereas on the left, that lone pair is going to be siphoned off by the NO2 group, making that more stable. So it's going to be less likely to act as a base. Okay? All right. Are any questions on those two examples? All right. If not, let's take a little break here. 10 minutes, and then when we come back, we'll wrap up acids and bases and talk about Lewis, the Lewis definition. Okay.
To electron domain groups, are you specifically just talking about the more carbons there are?
Yeah, more carbon-based base groups. Yeah.
So over here, if we're comparing it, are you saying we have more carbons because of this one?
Yeah, that carbon is adding electrons to the oxygen, and
so
that overflow of
increasing.
oxygen. Yeah.
Okay.
And it wants to get rid. It wants to share it because this ring is actually. It also can withdraw electrons from it because you can move the bonds around. So that's why it does that. Yeah.
Okay. And then I do have a question. Why can't this bond create a double bond right here instead of?
Yeah, you could do that. I just want to illustrate that you're getting more negative charge in the ring, so and it's closer to nitrogen, so nitrogen can just pull those electrons away, and then use those as additional, basic power to activate.
But if I do make a double bond right here, I wouldn't be it won't be more than octet, right, for nitrogen?
Oh, you mean over there? No, then you could just move these electrons and then push that up to the carbon, so you don't break the octet rule.
Oh no, I was thinking actually moving that to that line.
Oh, that one?
Yeah.
No, why can't we do that?
Because it would be more than octet, right?
Yeah, nitrogen can't accommodate that many.
Okay.
Yeah, you're right.
Got it.
Yeah, hello.
The higher pKa number indicates a stronger acid or
The reverse. It's like pH, remember? Higher
I
pH
just wanted
is
to make
basic.
sure. I was like, I'm pretty sure, but I was like, wait, I'm sure it's different for that.
All right.
Oh, no, I have it. Yeah. You want one? The baby, it's his first game. He looks so mad. I don't know why he doesn't do it. He's mad. He's doing orca shorts. So how's his personality? He's like screaming a lot, but my nephew, my sister's kid, he watches him watch his cat. He just screams nonstop. He just screams. But he's like very sweet. He's very loving. He loves his mom's boy. He just wants to be held by his mom. I watched that Taylor Swift show. It's like extreme. Oh god, no, I could tell. The math, yeah, so it's
I haven't finished my homework yet.
Which one? The first one? Okay. All right. Do you want an extension? All right, I'll give you an extension. All right. Turn in by Thursday. Okay.
Yeah, I still got library all the time.
Yeah. Yeah. So this is on number. This auction already has a full octet, and I can't break any bonds because there's no double bond nearby. So if I were to break a bond, I would break a single bond. You know, and that we usually don't do that for resident structures. Unfortunately, yeah. That's why.
I was gonna be left because I like that sheep like rules for like
Rules? What do you mean?
having numbers like rules.
Oh, yeah. You have to do that by Yeah.
Oh, Maria.
Okay, got it. Thank you. All right, guys. Remember, if you need a homework extension, you're allowed 3 of them. Okay. So if something unexpected comes up, feel free. Don't be afraid. Ask me. I'll give you an extension. All right. Yeah.
Do you teach Chem 2A?
Yes, I
Are
do.
you one of the professors?
I am teaching it. Yeah.
Okay, so I am a tutor at the Student Success Center.
Oh, great. Yes.
And they put me. I never took Chem 2A. I just went to general chemistry, but they put me.
Oh, yeah. You should be able to answer your
But
questions.
I was wondering if you have like a schedule of like what we'll be learning.
Yeah, I can send you my syllabus. Just
Yeah?
reach out with me an email and I'll send you
Okay.
that.
Okay.
Yeah.
Perfect. Thank you.
Thank you.
So it wasn't like that. The last question got me. I know. I look at it and remember that's what I was saying for like 10 minutes. But acceleration, I don't really understand. I don't like how like one
One was, I know one. I don't know if I got it right. Yeah, I did well on the ball one, just I wrote that. Oh, that's good. No, I don't think, I feel okay. But did you see the whole thing? No. Yeah, I can just watch it. I just grabbed it.
Wait, so how far was the back home though?
But
I was like, and it's like an hour away from here.
Good outside.
was like,
I know, I'm going to
I was like halfway.
I went like the last 5 days because I have to remember everybody. And it's really outside. So like,
I'm just like, oh. But you were on Wednesday? Oh, yeah. So that's it's just great plans to do it outside.
Yeah.
Yeah, I know.
No, you're okay. I usually don't, I don't usually, give you points every day for the lecture. It's lab, I'm more that take off points. So yeah, you don't feel well. Yeah. All right, guys, let's continue here. All right. So let's finish up our discussion of acids and bases. All right. So we talked about the trends in acid bases, how to determine acid strength, base strength. Now let's talk about the Lewis definition. All right. So here are some terms I will introduce now, and then throughout the whole semester, I will refer to these almost exclusively, and I will no longer say if something's a Lewis acid or Lewis base. They are the terms: nucleophile, and the term electrophile. All right. So if you think phile, that means you have, affinity or attraction to something. Okay. So nucleophile in this case means a species that is attracted to another atom's nucleus. Okay. And electrophile means there's something attracted to an electron. Okay. That's what those terms mean. All right. So we have acids in this definition. They are electron pair. So when I say electron pair, I mean a lone pair of electrons. Lone pair acceptors. So the acids are accepting a lone pair to form some kind of bond. All right? And then bases in our case, they are electron pair donors. All right. So let me give you an example. So a classic example is taking this compound, borane. So this is borane, the simplest boron compound here. All right. So boron. Does boron like to form an octet? You might have heard about boron as one of those exceptions. Does it? No. So this actually, boron here, if we point to boron, it has an empty p orbital. All right? So that p orbital can actually accommodate another bond. All right? So this is what we call our Lewis acid. Okay? And in parentheses, we can put electrophile, and that's because it's willing to accept a lone pair of electrons. All right? So here it wants electrons. Okay? So you have something nearby. For example, this guy. This is called diethyl ether. All right, this is a common solvent. in organic. All right, common organic solvent. So what happens here? It can donate its electrons to the boron. Okay. And then the resulting thing you have here is boron will now be bonded to oxygen. And this is a complex, or like an adduct. The result of adding these two species here, you get this reactive species. And this is usually stabilized by these charges here. All right. So here, this is what we call the Lewis base. All right. And this is what we term as our nucleophile. All right. So here it's attracted by the nucleus of the boron atom. So it wants a nucleus. The nucleus is a source of positive charge. Okay. So the electrons are being donated to the Lewis acid. The Lewis base is attracted to the Lewis acid because it has a deficiency of electrons. And that's what we get here. Okay. So we can actually classify this as a Lewis acid-base reaction. And another way of thinking it is you have the terms electrophile and nucleophile to kind of give you little descriptions of what it's lacking and what it needs. And that's why they react. And you form this structure right here. Okay? So Lewis acid accepts an electron pair. So it's accepting these electrons from the oxygen. Oxygen is donating that electron pair. So the definition is kind of quite the opposite from Bronsted-Lowry, where we said proton donor and proton acceptor. Okay? All right. All right, so let's classify, like, how can you tell if something's a Lewis acid, when is it a Lewis base? Okay? So, let's go to Lewis acids. So there's a few kinds here. So you have some that donate H+. So anything that can donate H+. So for example, you have carboxylic acids, like acetic acid, OH, okay, like that. The organic acids, HCl, H2SO4, HNO3. Okay. The molecule we just drew a bunch of, phenol, that's what this OH here. All right. And then anything with an OH group or H bonded to an acidic or an acidic H. Okay. For example, CH3, CH2, OH. So these are all potential sources of that hydrogen. Okay. That's a Lewis acid. Any possibility that can donate H+, that's your Lewis acid. Okay. So let's just abbreviate here. So we have this category, metal ions. All right. So stuff like magnesium, 2+, iron, 3+, aluminum, 3+. So any metal ions. So see here, they're deficient of electrons, so they can still technically accept electrons. So metal ions is another example. And then if they're neutral, metal compounds. So we'll see some of these as part of reactions. Okay, so metal compounds. So the most common are aluminum trichloride, titanium tetrachloride, iron trichloride, and zinc dichloride. So those are some common ones we see. Okay, metal compounds, they are also Lewis acids because the metal themselves can still accept a lone pair of electrons. Okay, and then you're going to have some situations where you have an unfilled octet slash polarized carbon atom. So I'll show you 2 examples for this one. Okay. So here's an example of unfilled octet. You have a carbon atom that is positively charged. So that can accept electrons. And that's the classic, that's one of the main patterns we'll see how carbon reacts. It's partially positive or a full-on positive charge. And then Lewis bases can come around and bond to it. All right. So this is a generic class of what we call carbocations. Because it's carbon and it has a charge and it's a positive charge, so we call it a cation. All right. So air could be this, or can break slash reform octet. In this case, it'll be a double bond. Okay. So let me give you an example what that looks like. Like, I'll do in this next example, okay? So now let's talk about Lewis bases. Okay. So what I'm referring to here is this piece, is this group here, the double bonded O. Okay. So this is partially positive, so you can add Lewis bases to it, and then this is partially negative. That can act as a base, so it can actually accept a hydrogen ion. Okay. But let me just demonstrate what I mean by those partial charges, okay? So Lewis bases are any compound with atoms that can donate a lone pair, okay? So they're basically basic atoms, so basic atoms with lone pairs. All right? So any atom here, okay? But let me show you an example. Let's redraw that carbonyl or that C double bond O we had before. Partially negative here. The carbon is partially positive because of polarity. All right. So the partially negative tells us this will act as a Lewis. This is the site of the Lewis base. So this will add atoms here. So donate electrons at this position. Donate electrons, okay? At this position, at the carbon atom, so let's point to the carbon atom here. This is the position where it acts as a Lewis acid. Okay? That's where you accept electrons. So that's where you're accepting electrons. So you can add different groups to this carbon atom as long as you have a lone pair. Okay? And that's the chemistry we see for this compound. All right. But so as long as your compound has oxygen atoms, nitrogen atoms, and sulfur, they will all act as Lewis bases. So for example, let's say we have methanol. That's a Lewis base. A nitrogen atom example would be anamine, CH3NH2. And then sulfur, you could have something like this, CH3SH, where you have now lone pairs. All right? So as long as an atom has a lone pair, it can act as a Lewis base. Okay? All right. Let's do a few more examples. Okay. All right, so here's a common example of a Lewis acid-base reaction. Using the example we just drew. All right, so I have my H here. The H is electron pour. All right, so we could write here as electron pour right here. So this hydrogen is electron pour. Wants electrons. Okay, so let's just erase this part here. All right. This oxygen, though, it wants to donate. So we could put here for the oxygen, wants to donate. So it wants to donate these electrons, the oxygen here, okay? So that's why when we write this reaction, we're drawing the curly arrow notation. Oxygen is going to donate its electrons. These electrons are going to leave with chlorine, and this is what you get. An acid-base reaction where you have now protonated or added an H to the oxygen of this compound here. Plus, and now Cl has a negative charge because now it has all its valence electrons like that. Okay. So here, oxygen right there, Lewis base, and then the hydrogen in HCl is our Lewis acid. So this is another example of our acid-base reaction. All right, Lewis acid, Lewis base. Okay, but we can also apply these terms, like I said before, nucleophile and electrophile. Okay, so let's do another example. So this is an acid-base reaction. All right, so here we have a typical acid-base reaction. All right, did that R go through? No. Acid-base reaction, H plus is transferred. Okay, but we can actually apply this to a different class of reaction. Okay, so let's just draw an arrow here. Here's my other example. Another example. In this case, we're going to say this is a substitution reaction. Okay, so say we have our Lewis base, in this case, hydroxide. All right, and we're going to draw our Lewis acid. In this case, this is called methyl bromide. Lewis acid, and here's our Lewis base. All right, so it looks very similar to what we have here. Something has a lone pair, and then something here has something that's electron deficient, or Lewis acid, something is electron deficient and can accept electrons to form a new bond as long as the bond to bromine breaks, okay? So what happens here is the arrows are pretty much the same, except the atoms here are slightly different. All right, and this is how one way you can make methanol, but this is not the way you would do it, just because it's not economical at all. There's a cheaper ways to do it with CO2 and bromide here, like that. All right. So this is a substitution reaction. Why? Because the OH changed places with the Br. Okay, so that's another example, Lewis acid and Lewis base. All right. The base here, this will actually have a more specific name, nucleophile. And the Lewis acid, a more specific name is the electrophile. All right. Okay, that is chapter 2. Captain, what's up?
So why is it with this example, we took the entire CH3
Yeah.
and not just one of the hydrogens?
Okay, good point. So let's go back to this example. Let's draw some dipole moments here. All right. So chlorine, in HCl, chlorine has what kind of partial charge? Negative or positive? Negative, right? So partially negative, and then hydrogen, partially positive. So in this case, you're taking the partially negative atoms and you're going to bond to something that's partially positive, okay? Now let's take that same idea and apply it to CH3Br. All right. Now, between carbon and hydrogen, is there really any preference for partial charges? There might be, but it's usually this, right? Between hydrogen and carbon, their electronegativities are so similar that we usually don't assign them partial charges. All right? Now let's think about between carbon and bromine. All right, so bromine is slightly electronegative, more electronegative than carbon. So that's going to be partially negative. Okay? And how about carbon? Partially positive. So the reason why, well, we don't have to do that because that's a negative charge. But the reason why it's now the whole CH3 group is because of the partial charges. Carbon, in this case, is more partially positive. Okay? And bromine here, bromine still wants to achieve an octet, so it's going to hog some of its electrons still and depart as bromide ion in the right. And that's why we transfer the whole CH3 group, because that whole unit is combined as the partial positive part of the molecule. CH bonds are so strong because they don't have a preference for electronegativity, so they share them quite equally. So there's really no charge separation to illustrate that a bond wants to break. So that's why they're still a unit. To break CH bonds, you actually need to use special reagents, and they're called catalysts, like palladium. So you can actually make it reactive. You can make that CH3 group, or take a hydrogen and take it off, but you need special help from other reagents. Okay. Are any other questions on that? We'll do more examples like this, so don't worry too much yet about that. It just falls under this definition. Okay? All right. So that is chapter 2. The next chapter, we're going to talk about alkanes. All right? And I'll just start now by just going over some functional groups, okay, that you ought to know. All right. So let's go over functional groups first. The reason why we go over functional groups is because we're going to go into naming alkanes. And I feel like if you go over the functional groups, you can kind of see how each of them are named. All right. So we're going to go over functional groups first. So the first group we'll go over is called the alkene. All right, so you might have seen this before. So the alkene looks like this. It's a carbon-carbon double bond. All right. And when you name alkenes, well, they change the naming like all the time. But the naming we'll stick with is what I'll teach you, okay? So usually you name an alkene with an ENE ending. So methane doesn't count. But say you have ethane, that's the alkene in your plastic water bottles, okay? So an example of this is H2C double bond CH2. So see, that's the most common alkene, and that's called ethene. All right. How about a triple bond? That's called alkyne. Okay. And it usually looks like something like this, where the lines to these carbon atoms, they can be either hydrogen or another carbon atom usually. All right. More basically. All right. So the ending here, you have the base name, and then the ending is "-ine", okay? So the most common one is this alkyne. So this is called ethine. There are common names to these, but don't worry about those too much, okay? So ethene and ethine. All right. Now we have an aromatic ring. That's called an arene group, okay? Or in this case, an aromatic ring. All right. And usually it looks like this. And then you can have multiple things attached to it. It doesn't have to be carbon and hydrogen, but usually usually it's hydrogen. But these rings can be in the center of a big compound and be bonded to multiple things, okay? So the name ending, there's none, so don't worry about this benzene here. It really has no influence on the name. And then the most common one here is called benzene. All right, so that's what benzene looks like. All right. All right. So if you have a halogen, we call it an halide or haloalkane. All right, and it usually looks like something like this. You have a carbon atom. Here's X for your halogen. And then since it's tetrahedral, I like to draw the dash and wedge bonds to illustrate the 3D shape. All right. And again, here, no ending really for haloalkanes. What's important here is that you name it like such. Chloro, this would be, for example, chloromethane, because there's one carbon, methane, like that. All right. So you see here the chlorine has no bearing on the name. It's still named as a generic alkane. All right. All right. Alcohol though. Okay. So when things have ending names, we say they have priority in naming. Okay. So alcohol would be an example of that. It looks like a haloalkane. You might think you would just call it alcohol methane or something, or hydroxymethane, but we don't call it that way. So there's a specific way we name it. Okay, so the ending here is ol. And if we take this example, CH3OH here, that's called methanol. So we took methane, drop the ending after the N, and add OL. That's methanol. Okay, so we'll learn about these names throughout this class. All right, the most common ones we'll probably name are haloalkanes, alcohol, alkenes, alkynes, ethers, sulfides, and I think that's it for this class. Okay, but let's just go over a few more while we have time here. Ether. All right, ether is like alcohol, except you have two carbon atoms grouped together. All right, so the ending here is just the name ether, okay? So if there's no hyphen with the ending name, they're separate words, all right? So look at this example. CH3, OCH3. All right, this is called dimethyl, because there's two of them, the two CH3 groups. And you put a space here, ether. So you just name the alkyl groups, or the carbon chains, and write the word ether. That's dimethyl ether. All right. So let's do a few more. Let me just get through these phosphates ones, and then if you guys want, if you stay behind, I'll give you your quiz if you want it. All right, monophosphate. So these are important because where do we see phosphates from? Biology, right? ATP. So this is where it comes in. All right, monophosphate. So like, adenosine monophosphate. That's where you could see these phosphates. You have one phosphate group like so. All right, so we just get this name phosphate. All right, an example of this is CH3, O, PO3, 2 minus. So the 2 minus are from those oxygen atoms right there. All right, so this will be an example of methyl phosphate. All right. And then the other one is diphosphate, okay? And then you could have many other kinds of phosphate, like triphosphate, but those aren't commonly encountered in organic. In biology, they probably are. It's just ATP. Maybe that's why we don't classify them, because there's like only one known example of that. Usually ATP and some derivatives that use phosphates. All right, so if that was one phosphate, diphosphate, you're going to have two of these groups linked together. All right, so this is a diphosphate. All right, so for example, CH3. So the oxygen comes first. That's because that's the oxygen that links the carbon group with the phosphate group. P2O6 3 minus. So this would be an example of methyl diphosphate. All right, so let's end it there. Stick around, I'll give you a quiz. Okay, so let me disconnect this.